I need to fill in a couple of key mathematical pieces for us. The act of calculating derivatives of vector valued functions is not a difficult task at this point in our calculus life, but let me add a little bit more support to what we've done already. If we had a two-dimensional vector valued function, so r of t has two function components, the definition of the first derivative should be very familiar to you. It is also known as dr dt, the first derivative. It's the limit as delta t approaches 0, r of t plus delta t minus r of t divided by delta t. If we follow this substitution, that's what the derivative of a function was in first semester calculus. You may not have used delta t as your notation, but very frequently we used some delta value, some change was approaching 0. If I do the substitution, limit delta t approaches 0, if I do it separately, well, this is f of t plus delta t minus f of t over delta t, and g of t plus delta t minus g of t over delta t. And yes, I distributed my scalar down here in advance, and I performed vector subtraction in advance. I may be a little bit too over anxious to get to the punchline here, huh? But if you separate these and then subtract the like terms in the vectors, then divide the whole thing by delta t, you will get here. And my students, this is just the definition of the derivative of f and the derivative of g. It's not that fancy. Not that fancy. That's why it was possible to take the derivative of the term separately, and I didn't rush to show you this because you might have already fast forwarded this. I don't know how you observe videos, even if it is a requirement for a class. So this is one little section I wanted to add a little bit more light to. I'm going to kind of go back to our vocabulary we've been looking at for our next step. All right. So we have position, the graph itself, which is r of t, and then we have the velocity vector, which is the first derivative, but can easily be named v of t. And we have acceleration. All right, I'm just going to squeeze that in over here. Acceleration. I don't want to go down the page. You'll see why in just a moment. So acceleration would be the second derivative of position, or the first derivative of velocity. We've done that. I just wanted to make sure you had it on in one spot, and also just sort of emphasize that you need to be comfortable hearing and using these terms. Speed. So I gave an example where there was a graph that looks something like this, parabolic, but at this location there was a tangent vector called the velocity vector. Well, velocity is a vector, which means it has the direction and it has the magnitude. Speed is nothing more than the magnitude of that velocity vector. It's literally the length of that vector. It's not super difficult to calculate. Let's just do a short example here. If r of t is t squared comma e to the negative 4t, then the velocity vector is your first derivative, 2t negative 4 multiplied by e to the negative 4t. I did use the chain rule right there. So the speed I believe that some of you might have notations for speed. I'm just going to write it the word speed here. When you calculate the magnitude of that vector, 2t quantity squared negative 4e to the negative 4t quantity squared, that's going to be the root of 4t squared plus 16e to the negative 8t. If you were asked to calculate the velocity at a time t, there we go right there. That was not an algebra expression you were hoping to meet today, I'm sure. If I want to calculate the speed at time is 0, I could simply plug in 0 into this radical expression. 4 multiplied by 0, e to the 0 power is 1, so you get 16. That's going to be square root of 16. That's going to be 4. But if you wanted, you could at first calculate the velocity at time 0. Go back to here. 2 times 0 is 0. E to the 0 is 1. 1 times negative 4 is negative 4. And then calculate your speed as the magnitude of that vector, and it's a lot quicker to find the magnitude of a vector that you already know is 4 units long. But it didn't matter which way we approach the problem, we get the same result. If you still have to calculate more derivatives, you would leave t in as long as possible. If you are finished calculating derivatives, why not substitute and switch to numerical values? I like numbers. One more little connecting piece in this segment, at least, that I want to show you, and it is the definition of what is called a smooth curve. Smooth curve. Please recall from Calculus 1 that we had examples of curves that were not smooth. The absolute value function was not smooth at its vertex. There was a graph y equals x to the 2/3 power, looks something like this. There are many graphs in polar. Many graphs in polar. So in polar, we have the cardioid. There we go. It was not smooth there. So this is an example where the derivative might be undefined, but remember, we had graphs where, like for example, the circle clearly has a tangent line here. It's just the slope is undefined. Well, and this is a smooth curve. Well, to find out if a curve is smooth, then here are the conditions. So a curve is smooth at some point, we'll call it t sub 0, if the first derivative at t sub 0 is defined, so no undefined values there, and that first derivative cannot be what's called the zero vector, or in this case 0, 0 if it's two-dimensional. This zero vector would be an instance where you would see these not smooth points or sharp turns when that takes place. We won't heavily delve into the continuity and some of the analysis part of this vector function in this type of course, but it's certainly something that a math major could study a lot more of later on. Okay, one more little segment. We're going to meet our first integral of the term. It'll be exciting.